Hello students, this video is about circumcenters. It's the 9th lesson in the 5th unit on triangle centers. We're going to take all of the stuff that we learned about during this unit, all of the stuff about perpendicular bisectors and all of the other lines, and try to combine them into the centers of triangles. And when you draw three perpendicular bisectors to a triangle, the point that they meet at is called the circumcenter. You remember that from all of my children are bringing in peanut butter cookies. The PBC stands for perpendicular bisector circumcenter. Let's take a look at the learning target. The learning target says we're going to be able to determine the coordinates of a circumcenter, like the x and the y, by applying its properties to coordinate grids and diagrams. So we're going to be looking at the coordinate grids, like the xy grid, and also diagrams, like the diagram that you see underneath here with no coordinates attached to it. First, let's take a look at the definition of circumcenter, which you already know, but let's formalize that definition. If three perpendicular bisectors of all three sides of a triangle intersect, that's what they're doing here. These are perpendicular bisectors and they intersect at one central point. How do we know they're perpendicular bisectors? Well, the perpendicular part is proven because of these little boxy things. Those are right angles. So we know that this line, the red line, is perpendicular to that side. This line, this other red line, is perpendicular to this side, and this red line is perpendicular to this side. How do we know they're bisectors? Well, recall that a bisector is going to hit a line segment at its midpoint. So if that's the midpoint, that means that this side and this side are congruent to each other. In other words, this half is congruent to this half. And then similarly, this half is going to be congruent to this half, and this half is going to be congruent to this half. So we know they're perpendicular bisectors because just that, they're perpendicular to the lines, and they bisect the lines. Fantastic. And they all meet together in the center in this one point called the circumcenter, a special, different center than all the other centers of triangles. So that intersection is called the circumcenter, like I just said, where each side of the triangle is cut in half at a 90-degree angle. The circumcenter is sometimes inside the triangle. Why do we say sometimes? It looks like this circumcenter is in the center of the triangle, or inside the triangle. Well, it turns out that there are some instances, there are some types of triangles for which the circumcenter lies either on the edge of the triangle or outside the triangle. Well, it turns out that the location of the circumcenter depends on the type of triangle it is, specifically the type of angles that the triangle has. For example, an acute triangle has a circumcenter that is inside the triangle. You can see all of these are perpendicular bisectors, and they meet at a circumcenter which is inside the triangle. However, for a right triangle, that circumcenter is going to lie on the side of the triangle. Specifically for a right triangle, the circumcenter is going to be located at the midpoint of the hypotenuse. In other words, for this particular hypotenuse, this side and this side are going to be equal to each other, right? The midpoint of that hypotenuse. And then for an obtuse triangle, the circumcenter is located outside the triangle. So whenever you have an obtuse triangle, you know the circumcenter is going to be outside. Obtuse outside, that's how I remember it, O and O. And then for acute triangles, the circumcenter is inside the triangle. I don't have a cute way of remembering it other than acute triangles inside. Haha. All right, so that's just something that you should put in your memory banks. Another thing that you have to remember about circumcenters. Let's go back to the definition. Oh, by the way, thank you to Dorothy Evans of the University of Georgia for these graphics. Anyway, going back to circumcenter, we said that the circumcenter is sometimes inside the triangle. As I said, if it's obtuse, it's outside. And we also know that the circumcenter is equidistant to the three vertices of the triangle. Now here's what that means. Equidistant means equal distances. So that means that the circumcenter is equal distances from each of the three vertices. So here's how it looks in the diagram. So here I drew dotted lines to represent the distance between the circumcenter and each of the three vertices of the triangle. You'll notice that this dotted line, this distance, is going to be exactly the same measurement as this distance, and it's going to be the exact same measurement of this distance. So that circumcenter, that central point, is equidistant to the three vertices. That's not the case for the other centers of triangles. It's not the case for centroids. It's not the case for orthocenters or incenters. The circumcenter is the only one that is specifically equidistant to the three vertices of the triangle. How is that useful? Well, let's take a look at model problem number 1. In the real world, 3 students from Queens Metropolitan High School are planning a weekend charity event, and they need to select a location of the event. Since they're going to be traveling from home, all their homes are here, here, and here. They want to meet in the middle, which makes sense. They don't want one person to travel for longer than the other, so that they all travel about the same amount of time. If one student lives near Juniper Park, of course, Juniper Park over here. If one student lives near the Maple Grove Cemetery, which is down here in Kew Gardens, and if one student lives next to the Queens Zoo, which is over here in Corona, how can they find a central location to meet? So let's write a message to the students explaining what to do. That's the task. So sounds like we need a point that is equidistant from all three of these vertices, all three of these points that's in the middle. Sound familiar? That's right. The circumcenter is the point that is equidistant, equal distances away from the three vertices of a triangle. So write out that sentence and then come back to see if you got it right. All right, here's a sample of what you could have written to the students. We're telling the students that they should find the circumcenter. We're explaining that the circumcenter is the point in the triangle that's equidistant from all three vertices, the same distance away. And the step-by-step is here's how you do it. First, you're going to find the midpoint of all three sides. And then from each of these midpoints, we're going to draw perpendicular lines from them. And then wherever those perpendicular bisectors meet in the middle, that point is the circumcenter. Notice that this question didn't ask us to do any math, but sometimes on tests, on quizzes, on the geometry regents, it asks you for an explanation. And this explanation really shows that you understand that the circumcenter is the point inside of the triangle, or sometimes outside the triangle, where it is equidistant to all three vertices. And this sort of walks them through a step-by-step on how to create that circumcenter. First find midpoint, then create perpendicular lines, and then find where they intersect. This is actually going to help us with the coordinate grids that we're dealing with later on in the video. In this check for understanding number 1, it asks, in which types of triangles will the circumcenter not appear inside the triangle? Draw a picture to justify your response. Take a couple seconds to try this one, and then come back to see if you got it right. And you can see here, especially when a question on a test or a quiz or on the regions asks you to draw or sketch a picture, it doesn't necessarily need to be super perfect, but we can see that circumcenters are not inside the triangle. For right triangles, you can see that for a right triangle, it's on the edge of the triangle, so we call that the midpoint of the hypotenuse, right? And obtuse triangles, obtuse outside, right? The obtuse triangle has a circumcenter that's outside of that triangle. All right. Let's take a look at circumcenters in the coordinate plane. And you'll notice that we're following the same procedure that we outlined in the letter to the students for that student project problem. In order to find circumcenters in the coordinate plane, we're going to find and calculate the midpoint of two sides. That's what we told the students to do first, find the midpoint. And then calculate the slopes of those two sides to find equations of both perpendicular bisectors. That's what we asked the students to do, draw perpendicular lines from those midpoints. And then finally, last but not least, we're going to solve the two equations for the intersection point. Notice in this example, we're only asking you to find two different perpendicular bisectors. What's the reason? Well, if I take a look at this picture and I remove one of the perpendicular bisectors, those other two perpendicular bisectors still meet at that same point. We don't need the third perpendicular bisector to show us where the circumcenter is, because two lines intersect at one certain point. It doesn't matter whether that third perpendicular bisector is there or not. So that's what I'm using for the basis for this argument. All I need is two perpendicular bisectors intersecting at a certain point in order to find that circumcenter. That would be here in this case. All right, so that means you have a roadmap. You know we're going to calculate midpoint, we're going to find slope, we're going to write the equations, then we're going to solve. I'm going to give you an example of what that looks like here. In the model problem, it asks us to find the circumcenter of the triangle graphed right. Here's our triangle. We know it's an acute triangle. We can look at it and see that it's acute and not obtuse or right. So we can make the guess that this circumcenter, I should say, is going to be inside the triangle. Let's take a look at the steps. The first step, as we talked about before, is finding the midpoint of the two sides. We're going to find the midpoints of AC and AB. We're choosing these two sides. And why not? We'll just choose any two sides. By using that midpoint formula, and the midpoint formula is here, you should remember that it's x1 plus x2 over 2, y1 plus y2 over 2, and we're solving for m, which is the midpoint. In both of these cases, we're finding midpoints of the lines. We're finding first a midpoint of AC, and then a midpoint of AB. I color-coded them so that you can tell which one is which. So 9, 6 is the midpoint of AC, and 5, 6 is the midpoint of AB. And I went ahead and filled those in on the diagram here. Next, we're supposed to find the slopes of the two sides. We're going to find the slope of AB and the slope of AC. The reason we're finding those slopes is because we need perpendicular bisectors. The bisectors are going to go through these midpoints, but if they're perpendicular, they're going to have right angles. They're going to have negative reciprocal slopes. So our first step is to find the slope of AC and AB by using the slope formula, a very straightforward formula. So we found the slope of AC to be negative 3 over 2, and the slope of AB to be 3 over 2. Now what we need to do, since we're looking for perpendicular bisectors is we're going to take these two slopes and find their NRSs, which stands for negative reciprocal slopes. So NRS is negative reciprocal slopes. We start off with negative 3 over 2, which means we turn it into positive 2 over 3. And then we substitute that slope into y equals mx plus b using the midpoint as x and y to find the value of the y-intercept. Once we find that y-intercept, we write out the equation y equals mx plus b, y equals 2/3, which is the slope, x plus 0, which is the y-intercept. Then for the other perpendicular bisector, we already have the original slope. Now we need to find the negative reciprocal slope, which is negative 2 over 3. Next, we are taking that slope and the midpoint that we found for line AB, which is 5, 6, and substituting it into, you guessed it, the y equals mx plus b formula. Once we solve this, we get 28/3 is equal to b. Ugly number, that's okay though, because improper fractions are people too. So that's our y-intercept, and our slope was found already, that's negative 2 over 3. All right, so we did a little bit of work to find these two equations, and here's what the equations look like on the graph. So we've drawn in our two perpendicular bisectors using the appropriate slopes and y-intercepts respectively, and you can sort of start to see where the circumcenter is going to be. If you were to just look at this graph, you'd probably be able to tell that the circumcenter is going to be right about here, because that's where the two lines intersect. But in order to do this algebraically, like what we're doing here, we need to now find the solution of these two equations. Now remember, back from algebra, when you learned about this in the first place, when you're trying to find the solution of a system of equations, and that's what this is, a system or two equations graphed on the same graph. A solution to the system of equations is the point at which they intersect. So in order to find that solution, not on the graph algebraically, we need to set these two equations equal to each other. One thing that you should notice about both of these equations is that they're both equal to the same thing. They're both equal to y. Which means we're able to take both of these equations and set them equal to each other by simply saying, well, if y is equal to this nonsense, and y is also equal to this nonsense, then both of those things should be equal to each other. So that's the general idea of what we're going to do here. Let's take a look at what that work actually looks like. As it says here, we're going to find the intersection or solution of these two perpendicular bisectors by setting the two equations equal to each other, which is what we've done here, and then solving to find the value of x. Pretty straightforward. Once you know your algebra, we get x is equal to 7. That's not going to give us all of the information. It's just going to give us the x value of the circumcenter. In other words, the x value of the solution to the system of equations. In order to find the y value, well, we have a choice. We could substitute the x value that we just found into either one of the original equations. I decided to do it into both, just to show that it's going to give us the same y value both times. So my y value is going to be 14/3, and my x value is going to be 7, meaning that the circumcenter is 7, 14/3. Now, here's the reason why I wanted you to do this algebraically and not graphically. Looks to me like this point is very close to 7, 1, 2, 3, 4, 5, right? However, it's not exactly 7, 5. It's 7, 14/3, which is 1/3 less than 5. The reason that we're asking you to do this algebraically is because we're not looking for what the answer is close to. We're looking for what the answer is exactly equal to. All right, that's it for the video on circumcenters. Good luck studying.